Hello, Mr. Spensey. This is Mr. Spensey, the Stat Sensei, and working on classwork 4.3, Regression, Inference, Printout. I'm going to work through these problems in somewhat the order that they're presented. I may get a little bit out of order. We have a simple random sample of 9 students, was selected from a large university. Each of these students reported the number of hours he or she had allocated to studying and the number of hours allocated to work each week. A least squares linear regression was performed, and part of the resulting computer printout output was shown. All right, so out of order real quickly, if I take this number and divide it by, if I take the coefficient and divide it by 2.731, I get this for T statistic. And that means I have an upper value, and I guess I wrote that dyslexic. It should have been 2.96. So this should have been 2.96, and the lower is negative 2.96 because it's not equal. So what I did was I went to the calculator, and I went to second vars, TCDF, and I took my lower bound, I said was negative infinity. Well, excuse me, my lower bound I said was this value, 2.69 or 2.96, and here's how I did that. 8.107 divided by 2.731. And then I shaded up to infinity by degrees of freedom. We had 9 students, so 9 minus 2. And I get this p-value, but because it's 2-tail, I have to double it, so times 2. So that's where I get to 0.0208. And 8.107 divided by this will give me that value. 0.4919 divided by 0.1950 equals this value. So that's 2.52. It's a positive, so I'm shading up, but it's 2 tails, so I have to go both directions. Remember, the T statistic is centered on 0. So second vars, TCDF, my lower bound is now going to be the 0.4919 divided by 0.1950. And I end up getting 0.1983. I multiply that by 2, and I get 0.03966. All right, so that's my p-value for this. All right, so we'll use that later on. So it asks us to identify all the variables, and it asks us to write the least square regression line. If I write it like this, I don't have to define my variables more than I have. So this right here tells me my x variables. My x variable is work. There's hours of work. This is my slope. This is my y-intercept. And so when I read this, we're talking about hours of study. So hours of study, and make sure you have a hat on it, equals 0.8107, or excuse me, 8.107. The decimal point should be there, plus 0.4919 times the hours of work. This is my x variable. Explain the meaning of the slope. Well, slope is 0.4919 hours of study over 1 hour of work. So for every 1 hour increase in time spent working, there's a 0.4919 hour increase in the amount of time spent studying. And both are increases because it's a positive slope. All right. Explain the meaning of the r squared. Well, the r squared adjusted is just there to bother you. So we're concerned about the 0.4716. So 47.6% of the variation in the amount of study hours can be explained by changes in the amount of work hours. What is the value of the correlation coefficient? We're going to take that same 0.476 and take the square root of it, but I have to check the sign of the slope. The sign of the slope is positive, so my solution will also be positive. When I take the square root of that, I get 0.6899. So the correlation coefficient is 0.6899. There exists a, and this is really important, moderately strong, positive, linear, need those 3 words, relationship between work hours and study hours. What is the meaning of the S in the context of this? Well, they tell us S is 4.349. So the standard deviation of the residuals is 0.4349 and gives the amount of variation that we can expect from the predicted amount of study hours for a given amount of work hours or a given quantity of work hours. All right, so that's number one. Moving on to number two. Create a hypothesis test that provides a conclusion. Okay, so we're actually using the same information that we just had, all right? But we're doing a hypothesis test. So beta 1 equals 0, beta 1 does not equal 0. So there is not a linear relationship between work hours and study hours. There is a linear relationship between work hours and study hours. You must find X and Y. If you do it like this, you've done it. I wrote my sentences out and then I just labeled which was X and which was Y. We need to define our slope, the true population slope for the change in study hours for a 1 unit change in work hour. Our equation, T equals B divided by SB. So 2 times the probability that T is greater than 0.4919 divided by 0.1950 equals 2 times the probability that T is greater than 2.5225. And so I have that value, and we've already calculated that p-value is 0.0396. 0.0396 is less than alpha, so we're going to reject the null. Our p-value is 0.03966. We reject the null. There is sufficient evidence that alpha equal 0.05 to suggest that there exists a linear relationship between working hours and study hours. And we probably should come back and say there is a linear relationship between working hours and study hours. Create a 99% confidence interval. If I had not done the definitions above, I would need to do them here, but I've defined the slope, and I've defined my X and Y, so I'm not going to do it again. So slope plus or minus T star standard error of the slope. Well, we know our slope is 0.4919, that came from up here. And we know our standard error is 0.1950, that came from up there. So we need to calculate our T star. Well, our degrees of freedom were 9 minus 2 or 7, and we wanted to create a 99% confidence interval. So second vars, inverse T, parenthesis 1 minus 0.99, close parenthesis divided by 2. Degrees of freedom happen to be 7, or 9 minus 2, and we end up getting 3.499. So there's my T star. Then I have to solve this by hand, and I end up with a negative to a positive, which is interesting. That means 0 is contained. We're going to come back to that. We are 99% confident that the true population slope for study hours relative to work hours lies within the interval, and here it is. Because 0 lies within the interval, we cannot say that a linear relationship exists between study and work hours, all right, or between study hours and work hours. All right, moving on to part 3. A regression analysis on the relationship between average annual profits and millions of dollars of insurance companies and the yearly number of major natural disasters gives the following computer output. Use the computer output to determine the equation of the least square regression lines. Identify the variables used in the equation. Annual profits with a hat is my Y variable. And I know that disasters, natural disasters, is my X variable, which is right here. My Y-intercept is 420.727, and my slope is 0.2709. If I write it like this, I don't have to define the variables separately. Explaining the meaning of the slope in context. 2.709 profit over 1 disaster. That profit is actually millions. So for every 1 disaster that occurs, profit decreases, and it decreases because it's a negative slope, on average by $2.709 million. Then it asks us to explain the constant in context. Well, our constant was 420.727. If there were no disasters, the company would have $420.7 million in profit. Our R squared. Our R squared, once again, the adjusted we don't need. The R squared is 46.5. So 46.5% of the variation in profits can be explained by changes in the number of natural disasters. What is the correlation coefficient? Well, I need to take the square root of my R squared, so the square root of 0.465, but I also need to check the slope. The slope is negative, so I know my R will be negative. When I take the square root, I get R equals negative 0.6819. There exists a moderately strong, really important, moderately strong negative linear relationship between the number of natural disasters and annual profits. Calculate S and give its meaning in the context. Well, they did not give us S. So I have to go about this by taking the 930 and dividing it by 9 and taking the square root of that. When I do that, I get an S of 10.16. So the standard deviation of the residuals is 10.16 and measures the variation in profits from the predicted for a given number of disasters. Give the meaning of the standard error of the slope in the context of this problem. Well, in this case, our slope is 0.969. I mean, our standard error is 0.969. So the standard error of the slope is 0.969 because the slope is estimated from a sample. Other samples are likely to have differing slopes. The standard error of the slope quantifies the amount of variation in sample slopes that we could expect from different samples. Okay, but really you don't need any more context than that. All right. For the same problem, it says create a 99% confidence interval for the slope parameter, explain its meaning in context. Well, I have to go ahead and define everything. Well, I'm going to define it by writing the equation. So this will define my X and Y by writing the equation. And beta 1 equals the true population slope and is the expected amount of change in profits for a 1 unit change in the number of disasters. B plus or minus T star SB is my equation, where B is my slope from the regression, and SB is a standard error. My slope from the regression is negative 2.709, and my standard error is the 0.9694. So I need to go back and calculate my T star. Well, T star in this case, they wanted a 99%, and we have degrees of freedom of 9 because they give that to us in the problem. So with that said, I can go second bars, inverse T, 1 minus 0.99 divided by 2, and degrees of freedom happen to be 9. And I end up getting 3.2498. When I solve that, I end up with negative 5.85 to a positive 0.41413. So we are 99% confident that the true population slope for profits relative to disasters lies within this interval. Well, notice we went from negative to positive. So because 0 lies within the interval, we cannot say that there exists a linear relationship between profits and natural disasters. Finally, we need to run a hypothesis test. So in this case, beta 1 equals 0, and the alternative beta 1 does not equal 0. Beta 1 equals 0. There is not a linear relationship between profits and natural disasters. Beta 1 does not equal 0. There is a linear relationship between profits and natural disasters. Our equation is T equals B over SB, where B is the slope and this is the standard error of the slope. Because it's a two-tailed test, we're going to have to multiply by 2. So 2 times the probability that T is greater than, there's our slope value, there's our standard error, and we end up getting negative 2.7946. So we ended up with a negative 2.7946, and we ended up with an upper, so we also have to have an upper of 2.79. So here's what we need to do. We're going to go second vars, TCDF, and since we're going to end up with a negative, we'll go from negative infinity or negative 99999. Our upper bound is going to be negative 2.70909 divided by 0.9694. And our degrees of freedom are 9. And we get a value. But it's 2 tails, so I have to double it. So that's where this 0.0208 or 0.0209 comes from. With that said, 0.0209 is greater than our alpha of 0.02. So our decision is going to be to fail to reject. Our p-value is 0.0209. We failed to reject the null. There is not sufficient evidence at alpha equal 0.02 to suggest that there exists a linear relationship between profits and disasters. So we can say no linear relation exists at the 0.02 level of significance between profits and disasters. All right, so I should say between profits and disasters, natural disasters. I hope that helps. Thanks for watching and good luck to you guys. See you on the next one.